Okay, so here's our setup. We have these conducting rails connected by a resistor. And then this is also a conductor, but it's free to slide back and forth here. In this little enclosed area here then, I've got flux pointing out toward my eyeball. Look at our little vector dots here. As I move this bar, that's going to decrease the magnetic flux that passes through this region because the area is decreasing. Remember, flux is strength of the field times area times the cosine of the angle between them. So the three different ways we can change flux is changing the magnitude of B, changing the angle between B and our dA, or changing the area. Here we're changing the area. We're decreasing the area, so we're decreasing the flux. That's going to create a current that tries to stop us from doing that. So I've got all these little vectors pointing out toward my face. Those are disappearing as this bar comes over. The new induced magnetic field then from this new current will try to replace those ones we're losing. It won't be perfect. If this were a superconductor, it would be. Everything I lose, I would gain back. And I wouldn't be able to do this. Or I would get current flowing for free. It wouldn't cost me any work. But this is not a superconductor. So those little field lines that will be popping up won't quite cancel out what it is we're losing. But they will point out because the magnetic flux through this region is decreasing. Faraday's law or Lenz's law, they both say that the induced current tries to stop that changing flux, points in the opposite direction of changing flux, so that will point out. B points out to make up for the little outs we're losing. Right-hand rule says that will be a current flowing around like this. Curl your fingers around like this and your thumb points out towards your face. So the current is flowing around here. So part A, the current will flow through the resistor and through this whole circuit counterclockwise. Now what about the force over here? So I've got a current in this bar flowing up. B is pointing out. F equals I cross B, or points in the direction of I cross B. Use your right-hand rule. I cross B will point back this way. There's a magnetic force on this bar pointing back this way. I'm pushing that way. The bar is pushing back on me this way, exactly the same amount. The harder I push, the harder it pushes back on me. We're balanced out to keep this going at constant speed. So I have to do work in order to make this current flow. It doesn't flow for free. I'm doing a force times a distance. That's work. So if we wanted to find out what the rate of force is, I could figure out my force times my speed. That would give me power. Or another way to figure out my power, figure out the power going through the resistor. That's the same thing. The work I'm doing is being converted into heat by this resistor. So power through a resistor is V squared over R. Let's find V. Let's find our induced EMF. So the induced EMF is epsilon equals, and I derived this in the lecture video, VBVL. So multiply all that together. The induced EMF, the voltage drop across this resistor, is 1.371 volts. Then the power, V squared over R, 3.85 times 10 to the negative 2 watts. That's how much, that's the power output I'm doing, and that's being converted into heat, or depending on what kind of resistor this is, if that's a light bulb, that might be converted into light and heat.